We're here today to talk about what happens when you work on a project and forget to write tests, and then a few months later you suddenly discover that you might actually need to have written tests for the stuff you've written. My name's Chris. You can contact me through the Twitter handle that's cleverly hidden on my front slide, or via the email address you can see plainly hidden on the slide. I wrote the abstract for this talk quite some time ago after spending 2 weeks fixing a 3,000-line piece of enterprise Java code. And this enterprise Java code was really barely tested. And when I tend to write abstracts for conferences, I do it because I'm confident that what I'm doing when I wrote the abstract was the right thing to do. And what I've learned since writing that abstract and actually writing this talk is that everything I thought was generally useful knowledge from what I did in the first place actually wasn't. What I hope is that this talk is still useful for you. At a past conference, I asked people whether or not they routinely tested their code as a matter of course. And when I did this, barely half the room put their hands up when I asked whether or not they unit tested regularly. And there's a culture around unit testing which, for people who live and breathe testing, people tend to have techniques for making code that they write work well under tests. And testing culture generally has people saying what they believe are self-evident truths that they use to make themselves feel good about doing tests from the very start. And I've got some pictures in these slides to help you feel how you're meant to when you see these phrases on it. Things like your test should not write to the database. Because writing to a database means you need to set up a new test with every test run you do, and that's really, really slow. And that you should avoid I/O because this makes your tests flaky and non-repeatable and slow. And that your tests should be fast so you can run them over and over and over again. Now these are generalizations that assume that the code that you write was written with testing in mind. So actually writing code that's designed to be testable from the start. Unfortunately, for many people who've written things without thinking about tests from the very start, these self-evident truths from people who love testing are often taken as an excuse to not ever go and write tests. And once you have code that can't make tests like this work, people say that your code is untestable, or that it's legacy. That's the word. More often than not, the statements like this motivate people to keep not writing tests rather than attempting to actually go out and test things. And so what I want to try and get across to you today is that if you have code that can be run, there is a way to write tests for it. The tests that you write may not be the ideal, but they're still tests. And from tests, you can go and improve your code base. Basically, that tests don't need to be perfect in order to be useful tests. And writing tests for code that wasn't designed to be testable up front, these tests will never resemble good tests. So what I want to impart to you today is that you can write bad tests. It will help you to improve your code and it will help you fix bugs. And if you're a testing enthusiast, the things I'm going to be talking about today are basically all of the wrong ways to test. But hopefully you'll come to accept that these are a valid approach if you need to adopt them. So to talk about testing done wrong, we first need to talk about how you do testing the right way, how you make code that people call testable. One popular way to do this is through test-driven development. Test-driven development is really, really popular at the moment, and it usually results in pretty good testable code. So basically, it's all about doing the bare minimum amount of work to make all of your tests pass. If your entire requirements are spec'd out by tests, so if you have a complete test suite that describes all of your requirements, then once your entire test suite passes, you have written all the code you need in order to satisfy your requirements. So you can see this is a really popular way of producing a complete test suite. There are other ways that you can use to write tests early in the process. You can make doing automated testing a mandatory part of your code review. So if you have a code review process, you don't accept code until tests are written. Or you can make it a policy to produce test cases when the bug reports come in. These all are good ways of making sure that you have adequate tests early on in your development process. So a bit of nomenclature for this talk. When we talk about testing in this talk, these are the definitions I'll be using. Unit tests are tests for small and isolated parts, and in general you will have lots of unit tests. And integration tests are tests that these parts all work together. Ideally you have very, very few integration tests because they're slow, and as we know and are told all the time, slow tests are terrible. And if you do a structured approach to testing, it usually results in units being written first, and unit tests being written first, and then integration tests being written later. Now, there are good reasons for writing tests early. If you've thought about testing from an early point in the process, you generally have well thought out interfaces with clearly separated concerns and interfaces that are easy to write tests for. Also, considering tests early often leads to state and I/O being separated from your business logic, and this is because having increased amount of states results in isolation issues in your tests, and I/O tends to make tests slow. And these things are generally terrible for writing tests. And so people like test-driven development because it's a way of making sure that you've actually planned out your tests as soon as your actual code comes into existence. But TDD also results in people with really strongly held opinions. You can tell it's a really strongly held opinion because there are capitals randomly put through this through the statement. But statements like this, "It is impossible by definition to do test-driven development after the code is written," is clearly a lie. They're not useful statements to make at all. They're there to make people who like test-driven development feel really happy about themselves without actually being useful for people who don't. And it also suggests that testing is a lost cause on old code bases. Now, Michael Feathers wrote a very influential paper in 2002 and also wrote a book based on the paper called Working Effectively with Legacy Code. And in this paper, he observed that very few people get to start on a greenfields project. That is one where you have a complete blank slate and you can define your entire architecture, how you lay out everything, and how you approach development from the start. What he also notes in this paper is that old code without tests often get left untested. And this becomes a huge maintenance burden into the future, because once code continues to be untested, you don't know whether or not you can change it, whether or not you can make things better. So what he also points out is that once you realize you have a lack of tests, that continuing this lack of tests is a bad idea, and that you should be aiming to transform your code base into one where you have a shot at early stage testing, and for easy early stage testing on future development. So, not everyone has the freedom to start their code base from scratch, and adopting a test-driven development approach isn't immediately possible for most people who don't have a clearly defined code base. So if you have code that's left without testing for long enough, it tends to develop undesirable features for implementing tests later on, things like poor interfaces. And when you have poor interfaces, this means you have to do lots of setup to test a single function. So you need to put in place a whole bunch of objects so you can provide data to given methods and stuff like that. Or even worse, having the only useful interface to a function being buried underneath multiple layers of function calls. So you need to rely on outer functions being correct in order to test the validity of the inner function. Another issue you might have is having a poor separation of concerns. This meaning you need to alter global state of your code base or of your running program in order to test the validity of something. Or, for example, going out and needing to call a network call or write to a disk or something like that in order to test validity. This is generally bad because you rely on the network being up or your disk not being full in order to run a test, which means you can get spurious errors. Having dependencies tied together, so needing to invoke code in one part that you're not interested in testing in order to test the validity of something else. Basically, these are all symptoms of coupling, and when your code is coupling, you don't have the units that you need in order to do unit testing that structured testing advocates. These tests only come about if your interfaces are well defined and discrete. And if you don't have these discrete units in your system, you can't do integration tests, because integration tests only make sense if you have unit tested parts in order to fit together. So if you've got old code that hasn't been designed properly, this standard structured approach to testing that everybody likes talking about doesn't really apply. And so when people realize that it's hard to easily write a test, in the general case, most people don't. I certainly didn't in this case. But this is still a bad idea to not go ahead and write tests. So what we need to do is define a testing strategy and figure out what that looks like if this unit and integration behavior that test-driven development recommends doesn't exist. When we're repairing old code, we need to do something completely different. So the start of a solution to this comes again from Michael Feather's paper. He coined the idea of test coverings, which is a different way about thinking about structuring your tests. So what is a test covering? It's nothing more than having a suite of tests that seek to produce as close to full coverage on the code that you're interested in testing. So writing lots of tests with the aim of getting coverage and not testing specific results, or not necessarily testing for specific results. So the most basic type of testing you can do is interface testing, which is basically where you look to see whatever interface you have available, put it under some sort of test harness, and then write test cases against that harness. So executing interfaces that you've already written, that already exist, and putting those under automated tests of some description. Now, often such tests will not give you particularly specific information about particularly specific bugs, but it will tell you whether or not your code has been spec'd correctly or is performing correctly, or it'll tell you if a bug somewhere exists. So what is an interface in this situation? It's basically anything that gives you okay isolation to the code you want to test. And when I say okay isolation, this is really a subjective thing. I'm basically talking about having minimal side effects compared with the other parts of your system. So most of what you're testing is the code that you're interested in testing, as opposed to having most of what you're testing be elsewhere. Because in most existing code bases, you probably won't be able to achieve full isolation on every single subsystem. In order to do that, you need to refactor. So the ideal for an interface test is being able to extract the code that you've already written and wrap it up in some sort of custom testing harness and run that under a test runner, like your language's preferred unit testing interface. Indeed, back in 2002, when Michael Feathers wrote his stuff on late stage testing, he thought that making a custom test harness was the most important thing you can do in terms of getting your code ready for testing. These days, if your code is easy enough to extract and wrap in another product, then go ahead and put in a harness, because it is still the best way to do it. But it's not the only way you can do it these days. For example, if your system has a web service or a REST API that exercises the right parts of your code, then calling requests against a web server or faking your requests using something like Django's requests framework is a perfectly fine way of doing a test harness. If you've got an interface exposed via a web API and you can get machine readable results out of that, great, you can run that and put that under test. These days, even if you only have a hard-coded user interface that's poorly separated from the rest of your code base, you can still use automation frameworks, things like Selenium and WebDriver if you've got a web-based thing. If you're doing mobile stuff, there's a Selenium equivalent called Appium. You can basically exercise your existing UI and put that under test. Basically, all you care about is putting stuff under isolation or getting as much of what you want isolated as possible. These days, any interface that lets you get tests in early is a good interface. So if you can write tests against a browser automation framework, then do that. Find whatever technology you can get that will let you write tests early. And even if you're in a language where there isn't a unit testing environment, you could launch an entire compiled executable from a test runner as a sub-process and feed arguments on each test run, and then manage your test cases that way. You can feed the output of that into a unit testing framework and still get reports in whatever you use to report your test outputs. You can basically still automate tests even if you don't have a test framework. And this is great. So a question about this. Is a test covering a unit test or is it an integration test? Well, in this case, it's neither. It won't give you unit level granularity, and it doesn't give you the guarantees that integration tests make. So unit tests can usually be run in isolation. They'll give you information about a specific function that you're testing. If you're testing a much bigger system under an interface test, looking at a single test's result might not actually make sense. So what do you get if you don't get precision about specific functions? It is confusing, yes. What a covering does get you is a thing called an invariant. You can observe invariants from the results of interface testing. Invariants are basically fixed observable properties of your system. A single passing test case is an invariant that you've induced upon your system. And when you have invariants, you can refactor code around that invariant because you can tell if behavior has changed. If you change your code, then a test failing after you've changed your code indicates that you've changed behavior. So basically, establishing invariants means that you can start refactoring with some level of impunity. And these invariants only exist on code that is under tests. So unit tests still give you invariants, but they give you invariants with much better precision. You can tell exactly what failed and you can tell how you made it fail. So like you can give your tests really specific names, or you can use assertion messages when you fail assertions that say exactly what failed, and you can give it specific test data that exercise the specific function, and you'd know exactly what goes wrong if your test fails. You know, test reverse string with single character fails, you know exactly what happens if you've got exactly what's going on if a thing fails. So if you make a test at the interface, you get useful information. That useful information is that a test has failed if a test fails. What it can't tell you is with any precision where in the code your tests failed. And indeed, you probably need to analyze multiple failing tests that touch similar code paths in order to reveal causes of failures. So this suggests it's often a good idea to adopt an approach where you have lots of tests where the lines of code that comprise the tests don't change, but the data that you pass into your system under test does change. So it gets you lots of data-based tests as opposed to lots of code-driven tests. And so even if you don't get tests that tell you direct fine-grained results, you still get tests. And that's a good thing, and you shouldn't be unhappy with it. Now, it's also vital to know what code is actually covered by these invariants that you create, because you can only justifiably refactor things if they're being run under tests. So an obvious metric you can use is simple line coverage. And simple line coverage is basically where it tells you what lines have been hit by test invocation. It's good for seeing broadly which bits of code need tests written, but getting big gains on lines of code as a metric is easy enough. Big functions with minimal branching, like this one, can get you, it can get you tens or hundreds of lines of code covered with minimal testing effort. So this 6-line function here, it only needs one test to achieve full coverage based on lines. Checking for branch coverage instead is often a much better bet because you can backtrack from points where there are branches to figure out what data you need to put in to make a branch light up. So basically unlit branches, so each of the ifs and the elses in this function, will give you clues about what data you need to pass into your test in order to make all of your tests cover all of your code. So in this case, you have a 6-line function down the bottom. The bottom one you can pass with one test, but the top one you need to give it 4 different tests in order to make all of the various branches light up for that function. In general, it's a really good idea to use metrics that indicate progress towards getting your code to a refactorable state, and one which gives you an idea of how much effort is involved in achieving coverage in a particular area. Lines of code is probably not something that indicates effort unless you have lots of flat branches, whereas branch coverage is often a good indicator of effort. Now, interface tests in general, this thing I've been telling you is a good thing. They're actually generally pretty terrible. They're complicated to write because you need to set up interfaces and write lots of boilerplate in order to get your code to be testable. They tend to be imprecise, so you need lots of them in order to gain useful information, and they will often be slow because they execute your entire system. So let's talk about how to make these slightly more bearable. So, if I/O and statefulness is embedded in the interface that you're testing, it's difficult to get rid of it. You need to have tests in place before you can go and refactor that. Usual techniques like mocking and faking only apply if you can extract an interface from some service level stuff that you're trying to write. So do the refactor, bringing the I/O and state out of your inner system after you've got the tests. So make that a priority. So the problem is that I/O tends to make tests very, very slow. And if you're working to refactor a system, you tend to want these tests you've written to be accessible so that people can run them frequently and know exactly when they've made a change that breaks stuff. So if your tests require you to do I/O, then it's likely that a large amount of your test is going to be spent setting stuff up, tearing stuff down. And this is necessary to maintain complete test isolation. But this comes at the expense of making your tests slow. So slow test suites are an inconvenience. People tend not to run test suites that take an hour because, well, it takes an hour and they can't write code while their tests are running. So they're going to get neglected. The trade-off is that you have something that's incomplete and incorrect. If you have an incorrect test suite, then you're likely to create further issues down the track, often from chasing down non-existent bugs that are induced under test but aren't present in the real system. So how you fix this? Measure absolutely everything that happens when you're running your tests. Know where it's tested and where you can save time in exchange for absolute correctness. One way that I've done this is to find tests that alter different parts of the environment and run those tests in groups. So find lots of tests that affect different bits of your system and put those in a given test case as opposed to grouping tests by functionality. Basically, this obviates the need for isolation and obviates the need for sanitization, which means you can run everything under the same, for example, database setup, which saves you setup and teardown time. It sounds like a terrible thing to do. It is, but it does make things faster in the meantime. You can run multiple tests in this same environment without hurting the overall correctness. And if you want to convince yourself that this is absolutely a correct approach, you can do things like run each test in your cluster 2 or 3 times in a different random order each time and see if things are introducing side effects. If you are introducing side effects, you'll get failures on some runs but not others. And this is a way to verify they're actually independent. And then if you really want to verify things, you can still run each test with full sanitization, say at 2 a.m. every night under your continuous integration, and get correctness across each test in a complete isolated system. Basically, don't make this your long-term testing strategy because it yields tests that are slow, tests that are non-specific and cumbersome to write in quantity. It should not be used as a testing strategy because broken interface tests tell you that overall behavior has changed, but not where it has changed. So you can use these as a way to test if overall behavior has changed as you change your structure. But it means you can still refactor whilst knowing that things haven't changed. So with that in mind, let's turn to refactoring. The big advantage of having your code covered by tests is that you can refactor with impunity. So let's look at a refactoring strategy that I've used once to stop relying on cumbersome interface tests. So Uncle Bob, who is an author on software architecture, describes code where frameworks, external I/O, and user interface all sits on the outside of a system, and core business logic sits on the inside of the system. And this is enforced by a thing called the dependency rule. And the dependency rule says that an inner layer of this architecture is not allowed to know anything about code that exists in any outer layer. So your UI framework can call into business logic, but business logic can't call into your UI framework. Brandon Rhodes gave a talk at PyOhio a couple of years ago. There are videos of it. You should check it out. On this thing called the clean architecture. And he provided a really nice, simple example of how this works in practice. So this is an example of showing the wrong way of refactoring. So in this, we've pulled out a method called call.json API, which is where all the I/O happens in this outer function. And we've left the processing code at the top level. Now, this refactoring approach means that you need to do a mock or a dependency injection of call.json API at testing time in order to test the outer function. So you need to replace that with something that doesn't call the network in order to test it properly. The alternative is to leave all of the I/O bound functions at the very, very top and pull out the processing into functions. And these processing functions, provided you can set up the data that's expected, are easy enough to test in isolation. You can do a test for build URL as a unit test. You can do tests for pluck definition as a unit test. And then find definition is something that runs as an integration test once you're testing it. Gary Bernhard gave a talk called Boundaries at PyCon 2013. And in this, he did something very important, which was to give the clean architecture a much cooler name. He called it Functional Core Imperative Shell, which is great because it actually tells you what it does. And in this talk, Boundaries, he basically talked about how to use this approach to think about structuring code so that you can minimize the amount of stuff you need to mock or need to fake when you're writing tests. And the idea is that if your core processing logic is expressed as pure functions, that is, ones that don't alter state, ones that don't call the network, you can unit test these processing functions thoroughly, and those tests will run really, really quickly, and you can run them whenever you need to and get instant information about whether your refactor has worked. And the integration tests just end up being the tests that execute at the top level of your system. This is where the I/O potentially happens. You have relatively few of these, so you only need to write fakes or mocks for relatively few things, and you can test actual I/O performance under a relatively central point. Now, the observation that's to be made with this approach is that it's not just an architectural decision. This functional core imperative shell approach also works at a local level. Any function that calls I/O is integration tested, and any function that doesn't can get unit tests. And what this means is that increasing your unit test coverage is just a matter of factoring out small unit testable functions. So an approach looks like this. Go looking for processing routines that don't touch the network, don't touch the disk inside bigger functions. Factor these out into testable functions, and even better, factor out the core inner loops of these functions so you can test the inner loop behavior on an individual level as well as an overall level. So as a rule, you keep your I/O at the top and you factor the fast code out into their own functions. And as you factor these things out, they're unit testable units, so you can go and write unit tests for them. And once you finish this refactoring process, these interface tests that you wrote at the start are actually, by definition, integration tests. This is magic. You finally have structured testing on unstructured code. So basically, starting with unstructured testing can still lead to good code coverage. And if you do it properly, you'll eventually have a jumping off point to do structured testing from your unstructured testing, which is really, really cool. So we end this talk with a short discussion of actually tracking down bugs. The first thing, test harnesses. You should consider how your code is going to be invoked when it's in production by a user. Test harnesses against existing code should be able to reproduce how anything can be invoked in your actual system. Otherwise, it's not going to let you be able to write useful tests. And if you can do this, then you can capture every bug report that comes in at the interface as a test and then spot regressions for existing bug reports, which is very useful. Now, writing new code to test an interface, because it requires lots and lots of setup, it can be hard to get an interface tested. So writing tests where you can expose data level cases as opposed to code-driven cases will get you a lot more productivity. In JUnit on Java, you can do parameterized testing. You can do the same thing in Python's unit testing frameworks. As a general rule, writing data, like in a spreadsheet, is something you can get anyone to do, and you can get anyone to do it quickly, whereas writing code is a specialist thing. So writing code to do tests is going to be slower than writing data. So try and make data-driven tests. It will be much, much quicker. And whilst interface tests can be slow to run and can be cumbersome, you clearly don't need as many once you start refactoring frequently and having lots of unit tests. But it's still justifiable to keep these tests around because they still test overall behavior, and that's a good thing. You just don't need to run them as frequently. You can run them nightly or weekly or something like that. And you can still get useful information out of these old tests that you wrote. So, when I wrote the abstract for this talk, I was undertaking a substantial refactor of very important code. What I have learned since then is that specific advice doesn't always apply, which is because everybody's code has its own mix of interesting issues that make testing difficult. And not every technique that I've discussed here might work in your situation. We have this thing called test-driven development, which is very, very popular. It works as a quality assurance process, but you can't really do it on existing code. But there are approaches that you can take where you define integration tests before you write your unit tests. Because having any tests at all means you can fix your code, you can refactor them, and you can end up with unit tests later on. So it's not impossible by definition to practice test-driven development once you've already written code. You just need to get to a point where you can write those tests. And that is the end. I'm here to take questions now. Anybody got a question?
Is test-driven repair your phrase or
yes, that's what I originally called this talk. Yes, I think it's a good approach to fixing your code base. And there's no reason why you shouldn't do it. Anyone else?
Just excellent talk.
Oh.
Thank you.
Yeah.
what sort of specific advice did you decide did you drop?
What specific advice did I drop? The code that I was doing that initially inspired this talk was testing against somebody else's or our integration against a third-party web service, and the entire test process ended up running against someone else's network service, and I found that speccing third-party stuff via tests is something that worked really well for us. So actually producing a definition for someone else's API via our own tests was a valuable thing to us. But I really don't recommend that because suddenly you get really flaky tests as opposed to just flaky tests because you're relying on somebody else to be getting it right that you have no control over. But I'm happy to share war stories on that particular thing later on if you want. Preferably with beer or something stronger. Oh, anyone else? Well, in that case, thank you all for coming along. I hope you got something out of the talk, and I'm giving a talk tomorrow on types, so come along to that if you enjoyed me speaking. Thanks for coming.